Welcome to Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials and nanoscience, who would be curating the RealSci_Nano Twitter account.
Hi everyone, today we have with us Corenlia Hofmann, who is a postdoc at the Department of Physics and Astronomy at the University College London in the UK. Hi Corenlia, how are you?
Hi Pranati, I'm very good. How are you?
I'm good, and after what you told me on the short podcast, I'm all ready to take a deep dive into your research and learning all about your science and your science journey and everything. So let's start. Let's start by understanding your scientific journey so far. So how did you end up in your current research field?
That's a bit of a story.
Yeah.
I have to start this, I guess, during my master's degree. I studied at ETH Zurich, and the master's degree there is not very structured. It's very loose, open, in terms that in order to graduate, you just need to have enough credit points in a set of categories. But these categories are not by topic. They are like theoretical core subjects, experimental core subjects, elective subjects, non-math or physics subjects. And so we were able to just pick and choose whatever fields or topics we were interested in, as long as they filled up enough slots in each of these categories. And I just started out really broad. I was taking particle physics and solid state physics and quantum electronics and anything I liked. Programming. Until I was like, quantum electronics, photonics, lasers, this is really cool. I really like these subjects. And it also helped that I got good grades in them in the exams. And so I started searching specifically for more like elective subjects in that particular field. And yeah, one day I received an email from a lecturer of one of those elective subjects, and I was like, hey, you did very well in that course. Would you like to do a master's thesis in our group?
Wow.
And so I got offered to do a master's thesis there, and thought, oh, why not? I really enjoyed the lecture, so let's try it.
Right.
And yeah, once I was in there, I just kind of continued. So I did my master's thesis in the group of professors like H, and then continued on to do my PhD there as well, and got into the field of attosecond strong field science.
Wow.
And continued ever since on this path.
Wow. That's so interesting, because you basically, science found you instead of the other way around, sort of. It almost sounds like that. The science, the research found you rather than you finding the research. So that is really cool. That's awesome. So we will talk, of course, about the attoseconds, and you already explained that in the short podcast as well. So your current research, the postdoc research that you're doing at the University College London, where would you say it falls in this big picture of materials or nanoscience? I know you don't possibly identify so strongly with material science or nanoscience, but what would be the relation? Let me rephrase and put it this way: that what is the relation between these two fields, like materials nanoscience and your attosecond field? So tell.
So there is a connection in terms of what we're looking at is how electrons behave while they are in bound states, or while they're being ionized, or when they're moved from one place to another. Because all of these electron dynamics happen on this extremely short time scale. And of course, all of these electron dynamics, they are also very important for certain material sciences, or like how materials behave, how they react to certain environments. And I said in the introduction part that I look at individual atoms. I shoot laser onto atoms, but that's my personal research. Within the auto science, there's also people who do the same or similar things with molecules, or with metallic surfaces, or with semiconductor materials, or all kinds of different targets. So we are kind of going into this more larger structures as well, and how electrons behave in these environments, to try and understand the behavior of these materials more in depth. But of course, what we're looking at is much on a shorter time scale, and also on a much smaller time scale, unlike the spatial regime, than what probably nanoscience or material science are used to.
Okay, yeah, that makes sense. I mean, yeah, at the end of the day, scientists or material scientists are trying to understand to a certain extent how the materials behave and why they behave in whatever way they behave. And to a certain extent, you're also trying to do a similar thing, but with atoms or with electrons.
Exactly. Yes.
I wouldn't call electrons or atoms materials, because that's wrong. But yeah, it does make sense, and I understand your science a little better now for sure. And I would say, yeah, I would, in my head at least, you're still in the materials or nanoscience field, because you're doing stuff with materials or parts of the material. So it all makes sense to me. As a trained material scientist, I try to find material science. I'm saying material science so many times, everywhere. So yeah, to me, to my brain, it makes complete sense, and it does make sense. Like, of course,
there is also, there's also one kind of subsection of auto science which works with materials which are kind of nanostructures.
Okay.
This is something that I've only do with my research interest in also using nanoparticles, nanostructures as an environment around which these attosecond science is done. So one particular aspect that is interesting there is, of course, if you have a metallic nanoparticle and you shoot a laser sort of nearby or onto a distribution of these particles, they will lead to local enhancement of the field. So we already come in with a strong laser pulse, and then we have these nanostructures which lead to local, even more enhanced fields. And so we have a spatial distribution, spatial non-homogeneous field, which can also create lots of interesting. There's been some research done into that, of course. So yeah. There's like these two aspects of it, of understanding how materials on a very microscopic scale behave, and also using nanostructures in order to modify the phenomena that we're interested in.
Right. Are you going in the direction of plasmonics, or like this, plasmonics? Is that what you're referring to, with specifically with the metal nanoparticles, where you shine the laser close to it or on it, that there is this enhancement effect, or am I completely off here?
So there is some plasmonic effects. There are also some like theoretical models which have been adapted for attosecond science, which originally came out of plasmon science to some degree.
Okay.
I'm not an expert in that, so
okay.
But yeah. But the type of things that we have been studied is, for example, like rather than ionization effects from a molecule or from an atom, there have been studies on like ionizations from a nanotip, from a tungsten nanotip, for example, which has some similar effects and some different effects.
Right.
Or the one study that I've been working on was just exploiting the fact that we have a spatially non-homogeneous field. So there is some kind of structure which leads to a local enhancement of the field. So depending on where you are in space, you have a different amplitude of the laser field. Which means depending on where an electron is flying, it sees a different strength of the field. And so depending on whether they'll go in one direction or in the other direction, they see a different field, and thus we see some asymmetries appearing, or we can modify spectra of whatever comes out of it because of that.
So fascinating. It's so fascinating. And
Yeah.
I mean, it sounds like you do a lot of, like your research itself is so cool, and then also the experiments that you do are so complete. These things, of course, you do think about it every once in a while, but in so much detail, and there is so much science behind it. Thinking about all of that is just blows my mind. And I mean, what I do want to ask you next is, I know it's a difficult question. If anyone were to ask me this question, I wouldn't be like able to choose, but I'm gonna try, and I'm gonna ask you to try. I mean, you're involved in a lot of interesting research projects. So if you were to pick one that you're most proud of, or the most quirky or fun one, I know it's difficult, okay? But if you have to pick one, could you pick one and explain it to us in super simple words in the section we call In Other Words? You can pick two if you want. Okay, you can pick two, okay?
Yeah. Since you mentioned like in other words, that draws my mind to something that is not exactly a core research project of mine, but it's just something that I did on the side, which I quite liked.
That's fine.
It's trying to explain my research to people who don't have any physics background at all. So it started out from having school kids visiting our labs, and it was my job to try and explain, what are we doing here?
Very simple, very easy, right?
Yeah, easy. Let's just explain quantum mechanics to kids who have never done physics. And so I had to think for a while, like, how am I going to do this? And in the end, I thought, okay, let's just abstract it to a classical equivalence. Because at least if I try to explain it with the classical equivalence, it's something that they can have an intuitive connection to it at least. So first I had to explain what is an atom.
Right.
For which I basically used Bohr's model of an atom and draw kind of the connection to, well, you have a core and there's particles orbiting around it, kind of like the sun with the planets orbiting around it.
Right.
And had heard about the solar system and had this image in their mind, so it was kind of something that I could draw from. Okay, now just make it much, 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 much smaller.
Right.
We also have a nucleus in an atom, and then the electrons, which are orbiting around the nucleus.
Right.
Exact force is a different one, and one is a quantum system, one is classical, but let's ignore that. Yeah, once I had this kind of image in their mind, I had a big bowl, kind of like a big salad bowl or something like that. And at the very center, at the bottom of the bowl, I glued a big glass marble to it and said, okay, this big marble, this is the representation for the core of this atom. Then I had a second, a smaller marble. And I basically told them, okay, the ball is now a representation of the force that keeps things on a circular orbit, a whole elliptical orbit part.
Yeah.
And I gave them the task of taking the marble and swinging the ball in a way that the marble would travel on the inside wall of the ball.
Uh-huh.
Kind of like, I'm from Switzerland, so there's this traditional thing of Talerschwingen. So any other Swiss out there will know what I mean. But yeah, so you just swing the ball very carefully in your hand so that the marble is just rotating around inside this ball held together. So you have kind of the representation of an atom in your hand.
Wow.
And while I was explaining all of this and then started talking a little bit about what is a laser, I gave the kids the task to try this, swinging around the marble and then handing the atom on from one person to the next.
Okay.
And it's just waiting for the moment where some accident happened and the marble would spill out of the bowl because they were not coordinated enough or not careful enough with handing it over or whatever.
Right.
And at first that seemed like, oh no, we failed. The marble flew out of the bowl.
Right.
But I was of course waiting for that moment because then I could say, see, that's what just happened right now for you is exactly what we do in our lab. We disturb this binding force with the laser, so kind of like shaking the ball out of rhythm, and the electron flies out of the atom.
Wow.
And so that's how I try to explain in very basic and very intuitive terms the kind of experiments that are being done in attosecond science to people who don't know anything about what is quantum mechanics.
That's such a cool experiment. I can completely understand why you picked this as the one of the proud of ones, which you can explain like in other words. This is so cool. This oh my god, this is so cool. It helps. It's so accurate. Also the way you start with the solar system and everything. For someone who doesn't have any knowledge of physics, any knowledge of what an atom is or anything at all, it just makes sense. Like, yeah, of course, that's what you do. It's you just do it at a very, very tiny scale.
Exactly.
But yeah, that is, oh wow. Yeah, that is cool. That is really cool. I understand your science in a completely different way now. And I also know how to explain it to people who don't have physics knowledge now. So I'm definitely going to borrow that and be like, yeah, just imagine you're holding a bowl and there is a marble or something like that.
Yeah, except we're just ignoring the fact that most of what we're actually doing in the lab is quantum tunnel ionization. So our marbles or our electrons actually fly through the wall of the ball rather than spilling over top.
Yeah, but now we are getting too let's getting too complicated.
Yeah. That's the quantum aspect.
Yeah, let's just stick with the bowl and the marble. That's all, and just trying to keep it rotating inside the bowl. Okay, super. So, Corenlia, I really hope your research experience so far has been wonderful, and it will continue to be wonderful in the future as well, ignoring the pandemic altogether. But if you had 3 wishes to improve your research experience, what would you ask for? And I'm not promising anything here.
Yeah, that's another hard question. The thing is, like, depending on which context, I could list different things.
Right.
And some of them are like tiny little thingies that don't seem all that spectacular, but they have an impact. And then other things are like huge structural issues.
You have 3. It's not just you have 3 wishes. I'm sure that helps.
Yes. So, one thing that I have seen in different settings, in different manifestations, is this mentality that doing a PhD is hard. but then taken into a direction where it's kind of been put as a prerequisite from supervisors or PI's perspective, which meant that when, like, it almost encouraged a situation where the PI felt responsible for making sure that their students were struggling in order to learn this important life lesson.
Yeah.
Which is just, it's a completely different thing to be struggling with your project and then have your supervisor on your side to try and help tackle this challenge.
Yes.
As opposed to trying to do your best and then your supervisor is like, oh, but the PhD is hard, you need to suffer, and I'm like, it's just not good.
It's not good. I mean, why go far? I had people, not my PI or not my PIs, but while doing my PhD, I had people around me, several researchers, be like, "Yeah, but your PhD, you seem very happy. That's not what PhD is about. You should suffer. You should be miserable in order to create science. It's like almost fantasizing misery to create." Art or create science, and I'm like, yeah, no.
Yeah.
So I completely understand.
Yeah, I feel glad with the supervisors that I had along my path that I never felt personally like I was in such a situation, but unfortunately I have like observed similar such situations, and it's just no. Suffering just for suffering's sake is not helpful.
No. And then getting out of your way to make your students suffer, that's just what?
I really don't understand it.
Yeah. No, I understand. I completely agree with you.
That was a tough one. Another one that's more like also kind of a structural issue, and that is very often I see that like institutes or universities or departments, they have this fancy anti-discrimination, respectful treating each other kind of policy. And it's very nice on paper or a statement on their webpage or something.
Yeah.
But then to actually put it in practice, that's where sometimes, or that's where the real struggle is, and that's what actually makes a difference.
Yeah. Yeah.
So yeah, I always feel like I've been so fortunate during my PhD with the environment that I was in, because we were part of a huge funding collaboration situation where the amount of money that the entire collaboration received depended on regular evaluations, which 1 out of 3 pillars was also equality, diversity work. So basically, there was money incentive in doing good work, in providing a good environment.
Always works.
And that's the one thing that in the end, I'm just convinced, like as soon as money is on the line, it can be done, and it can be done in a really good, positive, and productive way. But then in other cases, it was more of a struggle to even just talk about the topic in an open space. Right.
Yeah, so walking the talk instead of just talking, actually doing constructively something and educating people and providing tools to people who don't know how to have for example, diverse lab when they're hiring new PhD students. Maybe they don't know where to find people, because that's also something that a lot of people usually struggle with. Like, we don't know where to find be it diversity, equality, like I think it's all connected. So yeah, I completely agree with the second wish as well. Absolutely. Yeah. Third and last one.
Last one. Um, so this sounds like a completely obvious one.
Go for it.
People need appropriate tools to be able to do their work.
What do you mean?
I mean, it seems so evident and obvious, and of course you need the tools to do your work.
Right.
But with the complications of academic funding and budgeting and reimbursement regulations and all of this administrative details, sometimes, not always, of course, but occasionally there are really weird situations where like the best suited tool just happens to not fit into any standard box, and so you can't get it, and so you have to get something else that's not as appropriate.
Mm-hmm.
Sometimes even ending up costing more. Just because it just happens to fit in a box.
Right. Are you referring to a laser or like a scientific equipment, or?
That's both. I've seen cases for like scientific, for like, just hardware tools to use in your workplace, and
Right.
also for specific like funding situations of travel money or exchange, going on an exchange somewhere for a certain amount of time, different situations. I've experienced both on the like money funding for a certain thing or actual hardware.
Right. So anything that basically enables scientists focus on their science and have like collaborations or travel or buy new equipment or anything that helps with advancement of science, any kind of tools. Yeah, you're right. It does seem like, Corenlia, what are you talking about? Of course, people need that.
Yes.
But I see the point. I see what you're getting at. That it's just so complicated at times that you just end up either not doing it or not getting that particular hardware or getting the sub quality one, or so I understand what you mean. Yeah. That's an interesting one, actually.
It's a really complex thing, and I understand that there needs to be like rules and structures to how you give out money. And I honestly don't know really how to make it better, other than having a higher like baseline funding that is not tied to something specific.
Yeah.
So that it's more at the discretion of a PI to have just a certain margin of money to do these things.
Right.
Other than that, I wouldn't really know how to help this.
Right. Yeah.
So I know, like when you apply for a grant, you have to write your budget, and if something doesn't fit in the budget, you can't credit it to that grant. It's just,
And science doesn't always work that way.
Yeah. Yep.
It would be amazing if it did. Like, this is what I predict. And this is what is going to happen for sure.
If you write a proposal and then you actually do everything that you write in the proposal, wow.
Yeah, that would be, very, we should look into their brains. Like, did they time travel and be like, okay, how did you know that? But no, you're right. This is a very interesting one, actually. And I think we should start talking about it or pointing it out so that we will come to a solution. We don't have to have a solution at this point. But the first step is always to identify what the issues are, so to say, software, hardware, whichever. And then getting the minds together and fixing the issue or trying to find a solution. So that makes sense. All right? Yeah. Okay. So all three wishes, really interesting, really some things that should be voiced or some things that should be said. And you're right, it might seem like it's quite broad and at times it's quite obvious, but it does have it has a huge impact. It might seem small, but it does have, all three wishes of yours, they do have a huge impact. And I'm very happy that our scientists today, active researchers like you, are actually thinking about these things and actually trying to make it better, trying to make the research experience not just for yourself but also for the others around you better and for next generations as well. So I would like to believe that we are working towards it, and we will hopefully all three wishes after 5 years down the line, 10 years down the line, we would be like, yeah, of course, duh. It all makes sense.
I wish. I wish.
And speaking of future, what are you most looking forward to in the next 3 months?
3 months, I always feel like is like a very short time scale in terms of research.
Right. Sorry.
So I had to like separate it on a scientific level. I'm quite excited in just what we're doing right now because I started a new fellowship project basically right when the pandemic hit. So it was a really weird time. But I came to this new group with an idea in my head to try and take what I have done before and incorporate a really cool method that was developed in the group that I'm now a part of as of earlier this year. And I'm just really curious to see how that goes. How we can combine, merge, learn about the other method in more details, and see what we can get out of it when hopefully everything comes together and becomes even more powerful rather than hampering each other. We'll see. So that's the scientific side. On a personal side, within 3 months, I hope that I'm pretty sure I can go back home and just spend some nice Christmas time with my family, despite everything else that's going on. It'll be very small, no traveling around, no meeting extended family, but just I don't really want to spend Christmas all by myself here.
I'm pretty sure you'll be able to go back to, assuming Switzerland is where your family is.
Yeah. No, I will go back there. It's just a matter of organizing it.
Right. Yeah, I'm sure. I hope rather that you can spend a lot of quality time with your family and get charged up for 2021, which we spoke about. It's gonna be, everything's fine, nothing is wrong, everything's all's well.
Everything's going to go well. Yeah.
Everything's gonna go well. All right. So thank you very much, Corenlia. I learned a lot. We talked about, I feel like, everything under the sun. But before we let you go, I have one more question for you, which is, what do you think are the big challenges that are faced by the scientists today? It could be material scientists, nanoscientists, or scientists in your field, like physicists, whoever. What are the big questions that the researchers are trying to answer?
I'm going to give kind of a sneak peek of what will come later on during my curated week anyway. Okay. So one of the big challenges, besides the obvious this year, is obviously just this ongoing climate crisis, that we need to do something about that. And one aspect of that is, of course, having more efficient and having more stable renewable energy sources, out of which one of them is solar energy. So it just happens that if we understand charge transport, so how electrons move in complicated structures better, we can improve the efficiency of photovoltaic cells, for example. So it's like one of the possible dreamed about long-term goals of autoscience, and that we want to contribute a small part in that direction.
Wow, that's a really good one. I would not have imagined that this is an application to your research. This is so, yeah. Please do get it. We need it tomorrow.
The thing is, it's a quite a long-term thing. Like, I've seen a paper on ARC. Is it already out now? I'm not sure anymore. Where a group tried to model just the photosynthesis in a certain biological system, and they ended up using tunneling times, so one of the concepts out of attoscience, in order to describe how this electron moves like from one quantum well to the next in this whole biological system until it's recycled again. So better understanding of photosynthesis in the nature can help, and better understanding of how electrons move in semiconductor materials can help to make more efficient photovoltaic cells.
Ah, wow. So it's kind of like nature inspired? Kind of?
I mean, it's both sides at some point hopefully help each other.
Yeah, yeah.
Ideally.
Yeah, that sounds. I'm already looking forward to having that solar cell or panel installed in my daily life. That would be so cool. And then I can be like, yeah, Corenlia already told me about it a few years ago.
Yeah, well, I mean, in the meantime, the people who are actually working on photovoltaic cells right now, they are also doing a lot of work in making them more efficient and more easier to produce and all of that. So it's very much a combined effort.
Absolutely. All right, super. So thank you very much, Corenlia. I learned a lot. I enjoyed our conversation a lot and looking forward to having you take over the Twitter account. Thank you very much.
Thank you very much as well.
Thank you for listening. To know more about us, please visit our website, realscientistsnano.org, and follow us on Twitter at realsci_nano.